In March 1968, the Soviet nuclear submarine K-129 vanished in the Pacific Ocean. The U.S. military located the shattered hull resting on the abyssal plain, 3 miles down, a depth of 17,000 feet. The CIA needed the cryptography equipment inside, and to get it, they had to lift thousands of tons of steel straight up to the surface. The solution was a bespoke recovery vessel, the Hughes Glomar Explorer, built at the Sun Shipbuilding Dry Dock in Pennsylvania. The sheer mass of the hull required an entirely separate crane ship just to assemble its internal lifting mechanisms. Constructing a massive ship designed to steal a submarine required a cover story to keep Soviet intelligence away. The CIA partnered with billionaire Howard Hughes, who announced to the global press that he was building a deep-sea mining vessel to collect minerals from the ocean floor. Beneath the decks, the ship was entirely hollow. It featured a cavernous internal cargo hold and a hidden moon pool, designed specifically so the recovered Soviet submarine could be pulled up inside the vessel without ever being visible from the sky or the surrounding water. Because Howard Hughes was the public face of the operation, global media and rival corporations took the mining claim as a commercial reality. Fearing they were falling behind a billionaire's first-mover advantage, academic institutions began their own research programs, turning a fictional cover story into a competitive global industry. Lifting thousands of tons from 17,000 feet requires suspending over 3 miles of heavy steel pipe from a floating surface vessel. If the ship rises and falls with the ocean swell, that kinetic energy transfers directly down the rigid string. At those depths, the pipe will simply buckle and snap under its own mass. This diagram shows engineers decoupling ocean motion using a 630-ton gimbal system. It sat on 2 65-inch pneumatic rams acting as shock absorbers. By dynamically managing air pressure, the ship could rise and fall 15 feet, while the 10,000-ton payload remained perfectly stationary. During the actual recovery, the heave compensation systems worked flawlessly, but a structural flaw in the massive steel grapple caused the claws to shear apart. The section containing the targeted codebooks and nuclear missiles broke away, plunging 2/3 of the wreck back to the abyss. With the primary intelligence targets lost at the bottom of the Pacific, the espionage mission ended without its prize. Yet the mechanical success of the gimbal system proved that managing heavy vertical loads at extreme depths was possible, and corporations immediately began trying to replicate it for commercial use. Assuming the Glomar Explorer was genuinely mining the seafloor, engineers across the globe began competing in an industry that didn't yet exist. The focus narrowed to the clarion-clipperton zone, a massive area of the Pacific Ocean littered with polymetallic nodules. These are dense concretions of iron, manganese, cobalt, and nickel that have formed over millions of years in the crushing depths. Collecting them is one problem, getting them to the surface is another. Moving a dense slurry of heavy rock and seawater straight up requires a complex 2-stage riser pipe system spanning 4 kilometers. This visualization shows a free-hanging vertical pipe of that length. It is highly vulnerable to the dynamic response of surface waves. The regular motion of the platform induces oscillating sine waves that multiply along the length of the string. This parametric resonance is known as the Mathieu instability. Without constant tension, the massive steel riser will buckle and violently fail. To neutralize the instability, engineers use wet weight. They attach 300-ton submerged pumps to the absolute bottom of the riser. This permanent tension keeps the pipe perfectly taut, acting as an anchor against the oscillating forces above. Controlling a rigid steel pipe through miles of water solves the vertical transport equation. Operating heavy machinery at the bottom of that pipe introduces a completely different set of physical laws. The abyssal plain is not covered in solid rock or dense sand. The seabed consists of highly saturated, fluid-like bentonite clay and diatom sediment. This cohesive soil has a shear strength often measuring less than 2 kilopascals. It provides almost no structural support for heavy objects. Modern extraction requires subsea crawlers weighing upwards of 120 tons. If the ground pressure of the vehicle exceeds the bearing capacity of the sediment, it will suffer pressure sinkage. The multi-million-dollar machine will sink permanently into the mud and be lost. This interface shows the complex time-stress superposition calculations engineers must solve. They map the elastic modulus and viscosity coefficients of the sediment to design massive track footprints that artificially spread the 120-ton mass, keeping the machine afloat on a surface that acts more like liquid than solid ground. Once moving, the crawler uses hydraulic suction to lift the nodules. The intake nozzles must be mathematically sculpted to control fluid dynamics, gathering the heavy rocks without churning up a massive sediment cloud that would permanently blind the machine's optics. Success requires balancing a 120-ton mechanical footprint against a bearing surface that behaves like a liquid, forcing engineers to account for every second of sinkage to prevent total equipment loss. For decades, these machines were largely experimental. Today, the global push for renewable energy has spiked the demand for critical minerals far beyond existing terrestrial supply chains. High-capacity wind turbines require massive amounts of the exact rare earth elements locked inside those abyssal nodules. The global transition to electric vehicles relies entirely on securing reliable sources of nickel and cobalt for battery manufacturing. The International Seabed Authority is actively trying to draft the mining code that will govern international waters, but corporate entities utilizing domestic legal loopholes are pushing to bypass the slow regulatory process and begin immediate, large-scale commercial extraction. A fabricated cover story to hide a stolen Soviet submarine has evolved into an active, multi-billion-dollar corporate race for the ocean floor. Securing the raw materials required for modern energy infrastructure depends on mastering the exact same crushing darkness the CIA probed 50 years ago.